All right, so let's see what I was doing with this Bozeman function here. I was basically looking at, so if I call this, say, gamma 0 equal to y, okay, so then I should define, I could define, I mean, so in a cat minus 1 space, what I can do is I can define b, so if I take x, y, and xi, so okay, x, y in x and xi in boundary x, okay. So then I can take gamma to be the geodesic ray from y to xi, okay. And then, so I get a Bozeman function, b gamma from x to r. So then I can define b of x, y, xi to be this b gamma of x, okay, right? So what is this? This is basically, so let me draw it like this. In the notes, it's a bit different, but here's x and here's y. So I'm taking, this is my geodesic gamma from y to xi, and I'm taking basically points along this geodesic, okay, and I'm looking at the difference between, so plus here and a minus here, right? Yes, okay, yes.
Yes.
Okay. So so let me call this a limit of some function, say alpha t of x, right? These are functions of x. Alpha t of x is what? It's the distance from x to gamma t minus the distance from y to gamma t, right? Yes, as in this picture. Okay. Now, what is the level set alpha t equal to, let's say, for example, 0, all right? Okay. This would be the set where the distance from x to gamma t is equal to the distance from y to gamma t is equal to t, right? Yes. So in other words, this is the sphere around gamma t of radius t. Yes. Okay. So I take, so this is my gamma t. So I'm taking the sphere around this point, which passes through y. So this will look something like this. Okay. So I'm taking spheres of radius equal to t going to infinity, and the center of the sphere is also going to infinity. The center of the sphere is going to a boundary point. All right. Yes. Okay. Is the picture clear?
Yes.
So in the limit, so this is a sphere. This is a sphere of radius t. what happens in the limit, this converges to, these alpha t's converge to this b gamma. So this converges to b gamma equal to 0, right? So in the limit, what happens is if you do this in the disk, like say in H2, you'll get a circle tangent to the boundary, right? Which passes through y. Okay. So this is called a horosphere. So it's a limit of spheres of increasing radius. Okay. So this works for any level set. Instead of 0, if I had, whatever, if I had some number, say c, then this would be t plus c, and this would be t plus c, and this would be t plus c, and this would be c here. Is this clear? Okay. So, I mean, just an example, if I do this in x equal to the upper half space, right, and xi equal to infinity, and say y equal to the point 0 bar 1 at height 1, okay. Yeah, then what will I get? What will my Bosolman function be? What will my horospheres be? So here's the point y, and here is say x, and here's my gamma t. I'm joining it like this. So what will happen? Yeah. Any guess what will we see in the limit? Anyone? Yes. Are you there? Hello, are you there?
Yes, sir. Yes, yes.
Okay. So what will, so look, at time t, these level set of alpha t, you'll get a sphere of hyperbolic radius t plus c, right? A large sphere. So suppose x lies on the same horosphere. So suppose, I mean, so suppose x lies on the same sphere. So then this is a large Euclidean sphere also, right? It will be a very large Euclidean sphere. So what happens if I take a sequence of Euclidean spheres passing through a fixed point y?
Plane.
It will converge to what kind of plane?
The plane that is parallel to the base plane and passes through y.
Right, a horizontal plane, right? It will converge to a horizontal plane. Right, so what will your horospheres be in the limit? They'll be horizontal planes, right? They'll be horizontal planes. And once you know that, these are the horospheres, they're horizontal planes. Well, actually, I could have done this here. You see, this distance minus this distance, how do I calculate it? I know that if I go up vertically from x, right? Then if I look at this, if I call this point z, which is at the same height as gamma t, then I already saw that the distance between z and gamma t, this distance goes to 0. Right? Yes? This goes to 0 exponentially. Yes?
Yes. Yes, sir.
So therefore, this distance minus this distance is the same as this z distance minus this y distance, right? So in other words, it's just the difference of these two heights, this difference here, right? So it converges to the difference between these two. Is it clear?
Yes.
So, I mean, this z depends on t, so whatever. So I mean, distance x gamma t minus distance y gamma t. So by distance x gamma t is equal to distance x z t plus little o of 1 minus distance y gamma t, right? So if let's say x is equal to p comma, so e to the h, okay, if I write x in these coordinates, so then what is my zt? Zt is e e to the h plus t, right? Well, I mean, this difference is just no, sorry. Whoa, sorry. So wait. So gamma t will be 0 e to the t, right? This is at a distance t from y along the geodesic. Gamma t will be 0 e to the t. So this zt will be p bar e to the t, not e to the h plus t. P bar e to the t, right? Yes, is this clear?
Yes.
So then what is the distance from e to the h to e to the t? It's t minus h, right? Yes? Right? It's just t minus h.
Yes.
Okay. And the distance from y to gamma t is t, right? And then there's a little o of 1. So this just converges to minus h. Okay. So in other words, the Boseman function is just minus the log of the height. Okay. So Boseman function b x y xi, this is equal to minus the log of the height of x. Is this clear? Yes?
Yes.
So you can see that what does the limit look like? This converges to minus infinity if x tends to infinity, say vertically, right? And if you converge to any boundary point, then if you converge to a boundary point xi here, which is not infinity, then the height goes to 0. So log of the height goes to minus infinity. So minus of this goes to plus infinity, right? So this goes to plus infinity. if x converges to xi not equal to infinity. Okay? Is this clear? Yes?
Yes.
sir.
So in the ball, what does the picture look like? Here you have y and you have x. So basically, I have a horosphere which passes through y. So what is this horosphere? This is the set of x such that b x, y, xi equal to 0. By definition, it's a level set of the horosphere. Okay. All right. Now what happens if I'm inside the Boseman function? What is it? It's basically like the distance of x from xi, except the distance of x from xi is infinite. What we're doing is it's a renormalized distance function, right? It's the distance of x from xi minus the distance of y from xi. So both of those are infinite, but the difference is finite. You can think of it that way, right? Yes?
Yes.
Okay, it's two infinite quantities whose difference is finite. So if I'm inside this horosphere, then the Boseman function will be negative here, right? Here b will be negative as a function of x. And if I'm outside here, here b will be positive. All right? You understand? So these will lie on a larger horosphere like this, where the Boseman function is positive. Here it will lie on a smaller horosphere where the Boseman function is negative. All right? And the space will be foliated by these horospheres. You see? Okay. Yeah, so as I'm converging to any boundary point, which is not equal to, say, this xi, if I converge to any eta here, the Boseman function will go to plus infinity. All right? Is this clear? Yes? Okay. Any questions? Any questions? Yes, are you there?
Yes, sir. Yes.
It's okay. Yeah. So now let me talk about one thing which is called exponential convergence of geodesics. So this is a very important feature of cat-1 spaces. And this will make sense now that we've defined the Boseman function. So so suppose I have 2 points which lie on the same horosphere. Okay. So suppose I have xi in a boundary point and xy in x such that b xy xi equal to 0. All right. So that means they lie on the same horosphere. So here's x and here's y. All right. Yes. Now I look at the geodesic rays from x to xi and from y to xi, right? Okay. Then the claim is, if I look at the points at distance t along this, so let me call this geodesic ray xi equal to xt, t greater than or equal to 0, and the geodesic ray yzi is yt, all right? T greater than or equal to 0. Then the claim is the distance between xt and yt will go to 0 as t tends to infinity. In fact, these two will lie on the same horosphere also, on a smaller horosphere, you see. This is xt and yt. So how do we show that this distance goes to 0, right? How do we show that this distance goes to 0? So what do we have? We know that the distance from x to yt minus the distance from y to yt, this is going to 0, right? By definition of the Boseman function. Yes? So this distance is almost equal to this distance, right? Yeah?
Yes. Yes, sir.
So if this is t here, then this will be t plus some little o of 1. Okay. And let me call this distance here, whatever, some fixed distance. This is, say, c. Okay. So I'm going to do the following. Okay, let me see if I can do this properly. All right. So yeah, okay. So let me take a large T. So then I have something like this. And so this distance is T. This is T plus little o of 1. And now let me go a fixed distance S. So XS and YS here. Okay, so this distance is S now. And this distance is S, and this is T minus S, right? Okay. So let me call, what should I do? So 1 second, let me just think. So let me call this point Z. Okay, so this distance is, say, S also. Okay. And here, right. Okay. So here this is YT and this is XT. Okay. So the first thing is that basically, if I look at the angle theta here at YT, so I draw a comparison triangle. X bar, Y bar, YT bar, right? then this angle theta, I know what it looks like. Sine squared half theta is a big O of e to the minus 2t. Yes? Okay.
Yes.
Oh, let me do this properly for you. Okay, so that you see the details of it. We've done this calculation before last time. We did this sort of calculation. I'll just do it again. So fine. So this is t plus. This is t. Can you hear me?
Yes, sir.
Okay, all right. So so let me call this t plus little o of 1 is say t prime. Okay. So what do I have? Cos t is equal to cos h t minus t prime plus 2 sin h t sin h t prime sin theta. So, and I also if cos h d is equal to cos h minus plus 2 sin h t minus. Right? So this S and S, so this is cos h t minus t prime of 1. So this is 1 plus little o of 1, right? This first term. And this this 2 sin h t, this stuff is basically 2 into half e to the t plus t prime. So t plus t prime is well 2t. So 2 1 little of 1. I solve this by I mean this will be cos h c minus cos h t minus t prime. That will be so there's a half and a half. There's 2 halves here. And then again, there's a 2 and a half and a half. And I get yes. Yes, is this all right?
Yes.
Okay, so the e to the t prime will cancel with this e to the t prime. So I'll just get e to the minus 2s and this 2 half half, all of this will cancel. And I just get a cos h c minus 1, so plus little of 1. Okay, and there's a 1 here. So cos h d is 1 plus cos HC minus 1 e to the minus 2s plus little o of 1, right? Plus little o of e to the minus 2s. Plus little o of 1, right? Plus little o of 1, right? Okay. So here
Yes,
s is fixed. So that means that basically d, so that means that mod z ys is less than or equal to mod z bar ys bar, which is equal to d. And so this will be less than, so from this you solve for cos for d, and so for s large, it will be less than a constant times e to the minus s, right? Is this? Because cos hd looks like 1 plus d squared by 2. This is d.
Hello, sir.
Square instead law of 1.
Your voice is breaking.
Sorry, my Zoom disconnected. Can you hear me?
Yes, now it is clear, sir. But before your voice was like breaking. Very
Yeah, I know. Sorry. My internet is a bit unstable. Okay. Is Orkojit coming? Yeah, he's here. Okay. So yeah, okay. It's recording, right? So let me just share my screen. Okay. Okay. All right. So you see this. So this d is less than constant times e to the minus s, right?
Yes.
yes,
Okay.
sir.
All right. So that gives us the an estimate for the distance between z and ys. This is like e to the minus s times a constant. And now I have to check between xs and z, right? But this distance goes to 0 because I basically look at xt and yt. So I know this distance is bounded, right? Because they're both geodesic rays with the same endpoint in the boundary. So this is big O of 1, right? So this is big O of 1. And then if I look at the comparison triangle for x, xt, yt, then basically this angle at x will be very small and s is fixed. So the distance between xs and z will go to 0, right? Is it clear? Yes. Okay, so
Yes.
also distance xt, yt is big O of 1, right? This is given because they, by definition of the boundary, right? Because these are two geodesic rays with the same endpoint on the boundary, right? So this is big O of 1. So, and s is fixed. So this will imply that theta x of xt, yt, this goes to 0, this comparison angle, right? And since s is fixed, this will imply that distance between xs and z goes to 0, right? Is this clear? So that implies that distance xs z, so this is less xs ys, distance between xs, ys. So this is less than triangle inequality xsz plus zys. And xsz is little o of 1, and zys is less than constant e to the minus s plus little o of 1. So the whole thing is tends to constant e to the minus s. Is this clear? So therefore, distance xs, ys is less than or equal to constant e to the minus s. Where this constant you can explicitly work out. C is something like square root of cos hc or something you can take. This is good enough if this works. Okay. Is it clear? Where little c is distance xy. Is this clear?
Yes, sir.
Actually, you can take square root of cos hc minus 1. This is good enough. If you go through the proof, you'll understand this, right? Yes? Is it clear?
It is okay. Okay.
Because you get this cos hc minus 1 here, and you're taking square root, and so that's it. So this is the exponential convergence of geodesics, right? So it means if you start out on the same horosphere and you take these two geodesic rays, then it's like in what we had in the upper half space, right? These two geodesic rays, they'll converge exponentially towards each other, right? So a priori, we just knew that the distance between them was bounded. But if you start out on the same horosphere, then the distance between them will go to 0, in fact, right? Is it clear? So it's like what we see in the upper half space, right? In the upper half space, this horizontal is the this horizontal planes are the horospheres. If we start out with 2 points on the same horosphere and we take the geodesic rays going to the same boundary point, which is infinity, which is the base of the horosphere, then the distance between them, we saw it goes to 0 exponentially, right? This zt, gamma t, this distance goes to 0, right? Exponentially. So the same thing is happening in any cat minus 1 space. Is it clear now?
Yes, sir.
Okay. So, so this tells me that actually, since these geodesic rays are asymptotic, right? Any two geodesic rays ending at xi, therefore, the distance between them will go to 0. Okay. So if I take, say, x and y, if I take any geodesic ray gamma, then so for all gamma from 0 infinity to x, such that gamma 0 is equal to xi, we have this boson